a marker so that I can cut this up for YouTube. That is in. All right. Next up, game loop. Intent. Decouple the progression of game time from user input and processor speed. This is actually a big problem that I have in the Infinite Runner right now. If I were to run it, I think we're getting around 160 to 200 frames per second in the GG Easy Rust game. But if I put it into release mode, we're getting 2,000 frames per second, which is just a teeny tiny bit too fast to play because we're tying it to the processor speed. Motivation. If there is one pattern this book couldn't live without, this is it. Game loops are the quintessential example of a game programming pattern. Almost every game has one. No two are exactly alike, and relatively few programs outside of games use them. To see how they're useful, let's take a quick trip down memory lane. In the olden days of computer programming, when everyone had beards, programs worked like your dishwasher. You dumped a load of code in, pushed a button, waited, and got results out. Done. These were batch mode programs. Once the work was done, the program stopped. Ada Lovelace and Rear Admiral Grace Hopper had honorary beards. You still see these today, though thankfully we don't have to write them on punch cards anymore. Shell scripts, command line programs, and even the little Python script that turns a pile of markdown into this book are all batch mode programs. Mr. Halsey, hello, good morning. Also, this, that's really sad that they, that needed to be put in. It shouldn't be a thing. It shouldn't have to be a thing. Interview with a CPU. Eventually, programmers realized having to drop off a batch of code at the computing office and come back a few hours later for the results was a terribly slow way to get the bugs out of a program. They wanted immediate feedback. Interactive programs were born. Some of the first interactive programs were games. You are standing at the end of the road before a small brick building. Around you is a forest. A small stream flows out of the building and down a gully. Go in. You are inside a building. A well house for a large spring. I was going to say that almost sounds like Zork, but this is Colossal Cave Adventure, the first adventure game. You could have a live conversation with the program. It waited for your input, then it would respond to you. You would reply back, taking turns just like you learned to do in kindergarten. When it was your turn, it sat there doing nothing. Something like, so while true, wait until the command is read in from the command line, and then handle command, and just run the function for handle command. This loops forever, so there's no way to quit the game. A real game would do something like while not done and set done to exit. I've omitted that to keep things simple. I mean, we want to capture our audience, right? They can never stop playing, ever. Event loops. Modern graphics UI applications are surprisingly similar to old adventure games once you share their skin off. Your word processor usually just sits there doing nothing until you press a key or click something. While true. Okay, so we wait for... wait for event, then dispatch that event. Okay, so that's I didn't realize they were using a game loop essentially behind the scenes. That's actually pretty cool. Cookin', good morning. The main difference is that instead of text commands, the program is waiting for user input events, mouse clicks, and key presses. It still basically works like the old text adventures where the program blocks, waiting for user input, which is a problem. Unlike most other software, games keep moving even when the user isn't providing input. If you sit staring at the screen, the game doesn't freeze. Animations keep animating. Visual effects dance and sparkle. If you're unlucky, that monster keeps chomping on your hero. Most event loops do have idle events, so you can intermittently do stuff without user input. That's good enough for a blinking cursor or a progress bar, but too rudimentary for games. This is the first key part of a real game loop. It processes user input but doesn't wait for it. The loop always keeps spinning. So then that moves on to while true. So infinite loop, process input, update, and then render. And so this is very similar to what we have with the Rust game. We do have a process input function that's sort of outside of the update and render functions. We'll refine this later, but the basic pieces are here. Process input handles any user input that happened since the last call. Then update advances the game simulation one step. It runs AI and physics, usually in that order. Finally, render draws the game so the player can see what happened. As you might guess from the name, update is a good place to use the update method pattern. A world out of time. If this loop isn't blocking on input, that leads to the obvious question: how fast does it spin? Each turn through the game loop advances the state of the game by some amount. From the perspective of an inhabitant of the game world, the hand of their clock has ticked forward. The common term for one crank of the game loop are tick and frame. Meanwhile, the player's actual clock is ticking. If we measure how quickly the game loop cycles in terms of real time, we get the game's frames per second. If the game loop cycles quickly, the FPS is high, and the game moves smoothly and quickly. If it's slow, the game jerks along like a stop-motion movie. With the crude loop we have now, where it just cycles as quickly as it can, two factors determine the frame rate. The first is how much work it has to do each frame. Complex physics, a bunch of game objects, and lots of graphic detail all will keep your CPU and GPU busy, and it'll take longer to complete a frame. The second is the speed of the underlying platform. Faster chips churn through more code in the same amount of time. Multiple cores, GPUs, dedicated audio hardware, and the OS's scheduler all affect how much you get done in one tick. Seconds per second. In early video games, that second factor was fixed. If you wrote a game for the NES or Apple IIe, you know exactly what CPU your game was running on, and you could and did code specifically for that. All you had to worry about was how much work you did each tick. Older games were carefully coded to do just enough work each frame so the game ran at the speed the developers wanted. But if you try to play that same game on a faster or slower machine, then the game itself would speed up or slow down. This is why old PCs used to have turbo buttons. Does anybody remember that? Do any of you did any of you have a PC that had a turbo button? I had I think we went through two that had turbo buttons. New PCs were faster and couldn't play old games because the games would run too fast. Turning the turbo button off would slow the machine down and make old games playable. These days, though, few developers have the luxury of knowing exactly what hardware their game will run on. Instead, our games must intelligently adapt to the variety of devices. This is the other key job of a game loop. It runs the game at a constant speed despite differences in the underlying hardware. You were with a colleague cooking, having fun, looking at awful code. We saw a while true loop, which is very bad in that context. When I told my colleague that while true loops in game development is the normal way to do it, he couldn't believe it. Oh, you had a 486. Oh yeah, that would definitely have it. You'd be 66 100 megahertz switch or something like that. Yeah, that they did have those. I remember they were it was right next to the power button. So you had the power button, then right under that there was this little oval button. So it wasn't like a circle. And then it was you click in and it would stay in. And then you could click it to come out and then it was off again. And I guess they were opposite of turbo, right? They were like on when they were out and then off when they're in. It's sort of like, it always confused me because I would press the turbo button going like, oh, we're going to speed up the computer, and then it would slow down, which was interesting. But like, totally makes sense of what was happening. And it was just for games. That's super interesting. The pattern. A game loop runs continuously during gameplay. Each turn of the loop, it processes user input without blocking, updates the game state, and renders the game. It tracks the passage of time to control the rate of gameplay. Stacking, good morning! I guess good afternoon? It's not evening yet for you, right? It's just afternoon. They also had that weird circular key lock your father used to lock the PC up, but a pair of tweezers was enough to turn it off. Oh, yeah, and then Kensington or whatever took over all the locks for all the computers. Oh, you're on East Coast. Okay, so okay, then it's still morning for you. Yeah, it's only 9 or so for you then. Yeah, well then, good morning, Stacking. Welcome. Yeah, those Kensington locks are still easy to break. Like, nothing has changed in that way. When to use it. Using the wrong pattern can be worse than using no pattern at all. So this section is normally here to caution against over-enthusiasm. The goal of design patterns isn't to cram as many into your code base as you can. But this pattern is a bit different. I can say with pretty good confidence that you will use this pattern. If you're using a game engine, you won't write it yourself, but it's still there, unless you're using GGEZ, because that just gives me the delta time, but it just runs as fast as it can. For me, this is the difference between an engine and a library. With libraries, you own the main game loop and call into the library. An engine owns the loop and calls into your code. You might think you won't need this if you're making a turn-based game, but even there, though the game state won't advance until the user takes their turn, the visual and audible states of the game usually do. Animation and music keep running even when the game is waiting for you to take your turn. How do I feel about the new GitHub layout? When did it come in? Oh, I would need to, hold on, let me sign in really quickly. I've been needing to sign in anyways to this browser. Oh, and where are you? There you are. Okay, I logged in GitHub. You can come back now. Cool. So new GitHub layout. Like, this looks very similar to what I saw like, a couple weeks ago or so. Is it, where is it different? Because this looks, unless we're talking about something like within like last year's update where it changed to this. Oh, if I have to click on my profile and then enroll. Hold on. Profile. Is it through settings or something? It's not through edit profile. I guess settings. I have no idea where to look in here. I don't see it in like the first thing of the settings. Account, don't see anything there. Yeah, I'm gonna skip out of this. It's taking too long. They have 3 different features you have to opt in on. Well, I'll take a look at it later to see if I can find it, but I didn't find it like right off the bat with like going and looking at all these things. Oh, feature preview. That's what it is. Design updates enable. Repository refresh. So I only have 2. If I do that, refresh. Oh, this was that a circle before? I don't know. Doesn't look like it's changed too much. Looks pretty similar. The main change is the UI on the repo overview. Okay, so if I go into, let's go into our, go to Brooks builds. Okay, yeah, this is different. I mean, the README is still there. There's an edit button for it now. I mean, I like this. Now it shows the breakdown language instead of just like one language. Everything is very round. Yes, absolutely. I don't know. I mean, I don't hate it off the top of the bat. Like I still look like I can get all the information that I want to out of this. So, I mean, I'll have to play around with it a little bit. I don't use this interface like too much, except for like pull requests and other things, and it looks like I can still get to all those. But like I'll have probably more of an opinion in like a week or 2 after I use this for it. So ask me next week, and I'll probably have a better idea of like what I can say about it. Until then, let's get back to this. Keep in mind, the loop we're talking about here is some of the most important code in your game. They say a program spends 90% of its time in 10% of the code. Your game loop will be firmly in that 10%. Take care with this code and be mindful of its efficiency. Made-up statistics like this are why real engineers like mechanical and electrical engineers don't take us seriously. I mean, everyone makes up numbers and statistics. We do have pretty good ways of like verifying that though. You may need to coordinate with the platform's event loop. If you're building your game on top of an OS or platform that has a graphical UI and an event loop built in, then you have 2 application loops in play. They'll need to play nice together. Sometimes you can take control and make your loop the only one. For example, if you're writing a game against the venerable Windows API, your main can just have a game loop. Inside, you can call peak message to handle and dispatch events from the OS. Unlike get message, peak message doesn't block waiting for user input, so your game loop will keep cranking. Other platforms don't let you opt out of the event loop so easily. If you're targeting a web browser, the event loop is deeply built into browser's execution model. There, the event loop will run the show, and you'll use it as your game loop too. You'll call something like request animation frame, and it will call back into your code to keep the game running. Sample code. For such a long introduction, the code for a game loop is actually pretty straightforward. We'll walk through a couple of variations and go over their good and bad points. The game loop drives AI, rendering, and other game systems, but those aren't the point of the pattern itself, so we'll just call into fictitious methods here. Actually implementing render, update, and others is left as a challenging exercise for the reader. And like, I guess what we're going to learn here is probably how like delta time could be properly used. Potentially, maybe we can go like in not even use delta time. Run as fast as you can. We've already seen the simplest possible game loop. While true, process input, update, and render. The problem with it is you have no control over how fast the game runs. On a fast machine, The loop will spin so fast, users won't be able to see what's going on. On a slow machine, the game will crawl. If you have part of the game that's content heavy or does more AI or physics, the game will actually play slower there. So just because it's fun to show off, this is exactly what happens with the GGEZ Infinite Runner. So if I do cargo run release, we'll have to compile it for release mode, which shouldn't take too long because this is a nice, good machine. But I don't have anything to stop the game loop from to slow it down. So the game loop is just running as fast as possible. That's because GGEZ, while it is a game engine, it's also at the same time more closer to a library based upon his definition. So it both owns the game loop and doesn't own the game loop at the same time. So I'll just let this, it's almost done, but I'll let this run for a minute or so. Is it all 225? Let's see, who else has come in? WTF Blub, good morning. Oh yeah, you were letting me know where the feature thing was in GitHub. Yep, okay, so here it is. We are at 2300. This is not possible to play at all. So this is the reason why this chapter is important for us. Lots of FPS. Oh yeah. People would be like, oh man, I've got 60 FPS. I'm like, this is great. Other people, I've got 90 FPS. I got 120 FPS. Look at me. I've got 2,400 FPS. I am totally kicking butt with this. Too bad it's actually a little bit too much. Lost and wasted CPU power too. Yeah, absolutely. That turns up my my fans in the computer because it's actually just never waiting. Take a little nap. The first variation we'll look at adds a simple fix. Say you want your game to run at 60 frames per second. That gives you around 16 milliseconds per frame. As long as you can reliably do all of your game processing and rendering in less than that time, you can run at a steady frame rate. All you do is process the frame and then wait until it's time for the next one, like so. Okay, so we'll process the input, update the game, render, and then figure out, then wait some time. The code looks a bit like this. So 1,000 milliseconds divided by frames per second is the milliseconds per frame. So while true. So I think this is the beginning of the code that we can add in here. And I do have that the line thing set up, so you can do bang line, highlight lines if you want to ask questions or highlight problems that I have or anything else. Sometimes it makes sense to run games at high frames per second, just for the frequency and how update is called. Some people have higher accuracy at CSGO with 300 frames per second. Oh yeah, absolutely. But at some point you've got to cap it, or you got to make sure that it's smoother for them, but is literally not running faster for them, if that makes sense. Because if they can turn around a corner, see somebody and shoot, because they've got 15 milliseconds advantage over somebody else, then you've just added artificial lag, which is not good. Okay, so we got our while true loop. And so here's where, so we're going to get the current time. So this is essentially, so get the current time in probably milliseconds. So const now equals, so actually this is pretty easy in JavaScript. This is just going to be date.now, like that. That'll give us current time in milliseconds. We'll then run the process input, we'll run update. No. And render. Thank you for being so helpful, VS Code, but you're actually not. And then here's where it's like sleep and start. So in JavaScript, this won't ever work because we're asynchronous. I can't actually sleep ever. So this, let's actually do this. I'm going to convert this while function to a function game loop. We're not going to have true like this. Run payment process sounds about right for a game. Yeah, I guess in the modern games, but like I don't work for EA or Activision. I mean, it'll be fascinating. It's like, okay, well, next game pattern is microtransactions. If you'd like to see me compile the code, please enter 200 bits. Yeah, we're not going to do that. So if I want to do like, I can do a game loop, and then I'm going to do, this is going to have to be a function inside of here. We're now going to have to do start plus milliseconds per frame. Right, so milliseconds per frame is, what is milliseconds per, oh, it's this 1000 milliseconds divided by FPS. So that's how much we want it to be. So if I do something like const ms per frame equals 1000 divided by 60. Yes, that's going to be around 16.666 repeating. Let's put you at the very top. Okay, so if I have this, then we're going to start the game loop. We're going to get now. And at the end here, our start plus this minus then another current time with that. Okay, so here's how that's going to work. It's going to be super interesting. We're going to do oh crap, I just forgot the it's what is it? It's been so long since I've done the loops and the continuation ones. What's the one you can run once? Set timeout. Set timeout. And the function is going to be the game loop. And then the time of when we're going to run this is going to be our now plus ms per frame minus date.now, like that. So if we do this, then down here we can start, we're going to start the game loop. And we're just going to call game loop like that. Game loop will start. I will reach down here, and then it will then, after a very short period of time, 16 or so 0.66 milliseconds, it'll then restart the game loop again. Or I guess like it'll get the difference between that. The fun thing here is, because while this is recursion, it's not also true recursion. It's not going to be popping onto the stack and popping off. So we're not going to run into any kind of stack overflow with this either. It's just going to run forever. It's actually, this is my favorite recursive trick of how to like do tail recursion essentially. All right. The sleep here makes sure the game doesn't run too fast if it processes a frame quickly. It doesn't help if your game runs too slowly. If it takes longer than 16 milliseconds to update and render the frame, your sleep time goes negative. If we had computers that could travel back in time, lots of things would be easier. But we don't. Instead, the game slows down. You can work around this by doing less work each frame, cut down on the graphics, and razzle-dazzle, or dumb down the AI. But that impacts the quality of gameplay for all users, even ones on fast machines. Chantilly, good morning. One small step, one giant step. Let's try something a bit more sophisticated. The problem we have basically boils down to each update advances game time by a certain amount. It takes a certain amount of real time to process that. If step 2 takes longer than step 1, the game slows down. If it takes more than 16 milliseconds of processing to advance game time by 16 milliseconds, it can't possibly keep up. But if we can advance the game by more than 16 milliseconds of game time in a single step, then we can update the game less frequently and still keep up. The idea then is to choose a time step to advance based on how much real time passed since the last frame. The longer the frame takes, the bigger steps the game takes. It always keeps up with real time because it will take bigger and bigger steps to get there. They call this a variable or fluid time step. It looks like, okay, so we get last time, get current time. I notice that this is now outside of the loop this time. Oh, okay, so they're defining this to exist. Interesting. Last time equals current. Oh, okay, to sort of like start it all off. So let's go ahead and copy this in. So this is version 1. Version 2. All right, so we're going to do const the last time that we went through. Get current time. That is now date.now. I don't remember. Chantilly, did I say hello? I don't remember if I did. So hello. Date.now. That gives us that. So is this for avoid timeout, set timeout second parameter to be negative? I believe so, yes. Because if I set this and now it's like, oh, you have negative 55 milliseconds because you did something that took like a minute. Or I guess not a minute. You did something that took like 30 frames per second worth of time instead. Okay, so we get last time, then we're gonna get the current time. So const current time, so this is date.now again. Then elapsed. How long has elapsed since the last time? So const elapsed equals current minus last time. We're gonna go ahead and process the input. We pass elapsed into update. We then render, and then we update last time with the current time. And then we just continue on forever. Each frame, we determine how much real time passed since the last game update elapsed. When we update the game state, we pass that in. The engine is then responsible for advancing the game world forward by that amount of time. Say you've got a bullet shooting across the screen. With a fixed time step, in each frame you'll move it according to its velocity. With a variable time step, you scale that velocity by the elapsed time. As the time step gets bigger, the bullet moves farther in each frame. That bullet will get across the screen in the same amount of real time, whether it's 20 small fast steps or 4 big slow ones. This looks like a winner. Well, again, you're still going to have like the chunking happen, but I guess like if you only have 8 frames per second, it's not really, you have bigger problems. So the first time elapsed is almost like 0. Yeah, the very first time it's going to be millisecond. It should be 0 because it'll only be microseconds. And microseconds, I forget, it's like, is it like 1,000 microseconds within a millisecond? It's some insane number like that. The game plays at a consistent rate on different hardware. Players with faster machines are rewarded with smoother gameplay. But alas, there's a serious problem lurking ahead. We've made the game non-deterministic and unstable. Here's one example of the trap we've set for ourselves. Deterministic means that every time you run the program, if you give it the same inputs, you get the exact same outputs back. As you can imagine, it's much easier to track down bugs in deterministic programs. Find the inputs that cause the bug for the first time, and you can cause it every time. Computers are naturally deterministic. They follow programs mechanically. Non-determinism appears when the messy real world creeps in. For example, networking, the system clock, and thread scheduling all rely on bits of the external world outside of the program's control. It is fun to calculate collisions at very low frame rate. I kind of wonder. There's the old games that have sort of like the slowdown, like the bullet time method. Are they just slowing down the clock speed? Essentially, are they slowing down the frame rate, or are they just skipping some frames for like actually updating? I don't know. That would be interesting. I remember in Diablo, specifically Diablo 1, when you got items that would increase your attack speed, it increased the animation speed. So it didn't actually like do anything besides, well, the animation now plays this much faster, and bam, goes like that. But yeah, Max Payne, that was with bullet time, yes. Say we've got a 2-player networked game and Fred has some beast of a gaming machine while George is using his grandmother's antique PC. That aforementioned bullet is flying across both of their screens. On Fred's machine, the game is running super fast, so each time step is tiny. We cram like 50 frames in a second it takes the bullet to cross the screen. Poor George's machine can only fit in about 5 frames. 5 frames per second? Oh, no. This means that on Fred's machine, the physics engine updates the bullet's position 50 times, but George's only does it 5 times. Most games use floating point numbers, and those are subject to rounding error. Each time you add 2 floating point numbers, the answer you get back can be a bit off. Fred's machine is doing 10 times as many operations, so he'll accumulate a bigger error than George. The same bullet will end up in different places on their machines. This is just one nasty problem a variable time step can cause, but there are more. In order to run a real-time, game physics engines are approximations of the real laws of mechanics. To keep those approximations from blowing up, damping is applied. That damping is carefully tuned to a certain time step. Vary that, and the physics get unstable. Yeah, that's this is like the rounding errors with floating point games. These are really, really, really big deals in gigantic worlds. Especially if you can like fire bullets like across the arena. So I'm thinking like Planet Side 2, but then like Kerbal Space Program where you can like travel from the planet all the way to like another system. Like when you're doing the planning for like, okay, I'm gonna plan to go to the moon now. That is such a far distance away that the floating point numbers could be off. And it's like, well, here, apply this much fuel and you'll get there this time. And you actually apply that much fuel and it's like, well, actually, you were off by 0.001 milliseconds when you did your burn. So you're like way out there now because we didn't calculate that properly. Blowing up is literal here. When a physics engine flakes out, objects can get completely wrong velocities and launch themselves into the air. Oh, I've seen so many of those in games. Those are always fun bugs to find. This instability is bad enough that this example is only here as a cautionary tale. and to lead us to something better. I noticed that he doesn't even have, I guess that was this one. Play catch up. One part of the engine that usually isn't affected by a variable time step is rendering. Since the rendering engine captures an instant in time, it doesn't care how much time advanced since the last one. It renders things whenever they happen to be right then. This is more or less true. Things like motion blur can be affected by time step, but if they're a bit off, the player doesn't usually notice. We can use this fact to our advantage. We'll update the game using a fixed time step because that makes everything simpler and more stable for physics and AI, but will allow flexibility when we render in order to free up some processor time. It goes like this. A certain amount of real time has elapsed since the last turn of the game loop. This is how much game time we need to simulate for the games now to catch up with the players. We do that using a series of fixed time steps. The code looks a bit like, okay, so this is, okay, so we're going to start, this is version 3 now. We'll do const previous equals date.now. We're going to calculate the lag in here. Interesting. So, oh, you know what? These can't be const, can it? This has to be a let because they're being updated here. These are fine to be const, but you're going to have to be a let. Then we're going to have a lag. So 0. Then we start our entire loop. So while true. Then we get the current time. So const current equals date.now. Then we figure out how much is elapsed, same as last time. Const elapsed equals, this is our current minus the previous. Then we just go ahead and immediately set the previous to the current. Interesting. Okay, so previous equals to current. Lag plus equals elapsed. Okay. So we're going to keep track of the lag and add that in to figure out like how far behind are we. Then we're going to go ahead and process the input. But I notice we're no longer, oh no, process input. That's not update. So process input. Then, oh, interesting. So while the lag is greater than or equal to the milliseconds per update, where do we set that? Like, because we have milliseconds per frame, but I don't see. Note that the time step here isn't the visible frame rate anymore. Milliseconds per update is just the granularity we use to update the game. The shorter the step is, the more processing time it takes to catch up to real time. The longer it is, the choppier the gameplay is. Ideally, you want it pretty short, often faster than 60 frames per second, so the game simulates the high fidelity on fast machines. So here's where we can say, okay, const milliseconds per update. Here's where we can cap it. So you were mentioning in CSGO that we could have like 300 milliseconds per frame. So I could say something like 1,000 divided by, let's say we say on fast machines, your reward is 300 frames per second. That's the fastest that we can go on our computer. Now, if our lag is greater than or equal to milliseconds per update, then we run our update. So if our lag is greater than, so lag is plus equals to elapsed. How long has it been? So at the beginning, it's going to be almost 0. So we're not going to go through the while loop. Then the next, we're not going to update. Oh, wow. Okay. This is like almost the opposite of what I was kind of expecting to do. Let's see then. So in here, we'll run our update method. And then we're going to subtract lag. So lag minus equals the milliseconds per update. So we're going to wait until we have 300 milliseconds in, and then we'll go ahead and update. And then at the end here, we render. Yeah, there's a few pieces here. Yeah, definitely. At the beginning of each frame, we update lag based on how much real time has passed. This measures how far the game's clock is behind compared to the real world. We then have an inner loop to update the game one fixed step at a time until it's caught up. Once we're caught up, we render and start over again. You can visualize it sort of like this. Okay, we process the input, we update the game over and over and over again, and then we render. Note that the time step here isn't the visible frame rate anymore. Milliseconds per update is just the granularity we use to update the game. The shorter the step is, the more processing time it takes to catch up to real time. The longer it is, the choppier the gameplay is. Ideally, you want it pretty short, often faster than 360 milliseconds, so the game simulates with high fidelity on fast machines. But be careful not to make it too short. You need to make sure that the time step is greater than the time it takes to process and update, even on the slowest hardware. Otherwise, your game simply can't catch up. It just will never run the loop. Wait, is this saying now? Oh, okay. If I do this, it may never run this update function. If for some reason I can't get it to 300 milliseconds. No, it'll run once or twice, but it won't run enough to like, yeah, okay, so I see where the catch up now comes in. It won't run enough to actually like catch up to the real time. I left it out here, but you can safeguard this by having the inner update loop bail after a maximum number of iterations. The game will slow down then, but that's better than locking up completely. So if my lag gets way, way, way too big, so if I did something that then made this like, I don't know, 10,000 or something like that, then we're going to have like 100 of these. Interesting. So I can like do a count on that. Fortunately, we bought ourselves some breathing room here. The trick is that we've yanked rendering out of the update loop. That frees up a bunch of CPU time. The end result is the game simulates at a constant rate using safe, fixed time steps across a range of hardware. It's just that the player's visible window into the game gets choppier on a slower machine. Stuck in the middle. There's one issue we're left with, and that's residual lag. We update the game at a fixed time step, but we render at arbitrary points in time. This means that from the user's perspective, the game will often display at a point in time between two updates. Here's a timeline. Oh, yeah. Yeah, I see that. So like we're going to have update render. Like they start at the exact same time. But then we update. Like maybe they stay synced up for a while, but then eventually, yeah, render is going to get off because update is happening at a different time steps. As you can see, we update at a nice, tight, fixed interval. Meanwhile, we render whenever we can. It's less frequent than updating, and it isn't steady either. Both of those are okay. The lame part is we don't always render right at the point of updating. Look at the third render time. It's right between two updates. Yeah, and then at that point in time, it's just off forever. Imagine a bullet is flying across the screen. On the first update, it's on the left side. The second update, it moves to the right side. The game is rendered at a point in time between those two updates. So user expects to see that bullet in the center of the screen. With our current implementation, it'll still be on the left side. That means motion looks jagged or stuttery. So it's actually over here, but we see it over here. Oh man, if we're playing a game where you can actually, like with bullet time, or that you can actually see the things that are coming to hit you, that would be terrible. Because I guess I'm thinking something like Dark Souls, where you're trying to parry something, and you're using the visual animations to determine when to hit the parry button. But if you couldn't do that because they press the button and the visual doesn't update properly, that will make it insane to try to like time it. Your game won't be very playable. Conveniently, we actually know exactly how far between update frames we are when we render. It's stored in lag. We bail out of the update loop when it's less than the update time step, not when it's 0. That leftover amount, that's how far into the next frame we are. When we go to render, we'll pass that in. Oh, okay. So we can now render lag divided by milliseconds per update. So in here, lag divided by ms per update. We divide by milliseconds per update here to normalize the value. The value passed to render will vary from 0, right at the previous frame, to just under 1, right at the next frame, regardless of the update time step. This way the renderer doesn't have to worry about the frame rate. It just deals in values from 0 to 1. The renderer knows each game object and its current velocity. Say that bullet is 20 pixels from the left side of the screen is moving right 400 pixels per frame. If we are halfway between frames, then we'll end up passing 0.5 to the render. So it draws the bullet half a frame ahead at 220 pixels. Ta-da! Smooth motion. Of course, it may turn out that extrapolation is wrong. When we calculate the next frame, we may discover the bullet hit an obstacle or slowed down or something. We rendered its position interpolated between where it was in the last frame and where we think it will be on the next frame, but we don't know that until we've actually done the full update with physics and AI. So the extrapolation is a bit of a guess and sometimes ends up wrong. Fortunately, though, those kinds of corrections usually aren't noticeable. At least they're less noticeable than the stuttering you get if you don't extrapolate at all. This reminds me of what we do with our eyes, because we're constantly having a little bit of lag between our eyes or our ears and our brain processing the sensory information coming in. So if we see movement, like a ball being thrown at us and we're going to catch it, we don't actually see where the ball is in reality. We see where our brains know the lag and calculate where the ball is going to be, and then that's the information we see or hear, which is why if something suddenly stops, we could potentially get a little bit of vertigo because we actually see it in two places. We see where it really is now and where we thought it was going to be. It sounds like this is a simulation of that. In computers, we have to have the computer do that exact same calculation. Design decisions. Despite the length of this chapter, I've left out more than I've included. Once you throw in things like synchronizing with the display's refresh rate, multi-threading, and GPUs, a real game loop can get pretty hairy. At a high level, though, here are a few questions you'll likely answer. Do you own the game loop, or does the platform? This is less of a choice you make and more one that's made for you. If you're making a game that runs in a web browser, you pretty much can't write your own classic game loop. The browser's event-based nature precludes it. Likewise, if you're using the existing game engine, you will probably rely on its game loop instead of rolling your own. Okay, use the platform's event loop. It's simple. You don't have to worry about writing and optimizing the core loop of the game. It plays nice with the platform. You don't have to worry about explicitly giving the host time to process its own events, caching events, or otherwise managing the impedance mismatch between the platform's input model and yours. You lose control over timing. The platform will call your code as it sees fit. If that's not as frequently or as smoothly as you'd like, too bad. Worse, most application event loops weren't designed with games in mind and usually are slow and choppy. Use a game engine loop. You don't have to write it. Writing a game loop can get pretty tricky. Since that core code gets executed every frame, minor bugs or performance problems can have a large impact on your game. A tight game loop is one reason to consider using an existing engine. You don't get to write it. Of course, the flip side to that coin is the loss of control if you do have needs that aren't a perfect fit for the engine. Write it yourself. Total control. You can do whatever you want with it. You can design it specifically for the needs of your game. You have to interface with the platform. Application frameworks and operating systems usually expect to have a slice of time to process events and do other work. If you own your app's core loop, it won't get any. You'll have to explicitly hand off control periodically to make sure the framework doesn't hang or get confused. How do you manage power consumption? This wasn't an issue 5 years ago. Games ran on things plugged into walls or on dedicated handheld devices. But with the advent of smartphones, laptops, and mobile gaming, the odds are good that you do care about this now. A game that runs beautifully but turns players' phones into space heaters before running out of juice 30 minutes later is not a game that makes people happy. Now, you may need to think not only about making your game look great, but also use as little CPU as possible. There will likely be an upper bound to performance where you let the CPU sleep if you've done all the work you need to do in a frame. Okay, run as fast as it can. So this is sort of like, I understand that you're on a mobile device and I don't care. This is what you're likely to do for PC games, though even those are increasingly being played on laptops. Your game loop will never explicitly tell the OS to sleep. Instead, any spare cycles will be spent cranking the FPS or graphic fidelity. This gives you the best possible gameplay experience, but it will use as much power as it can. If the player is on a laptop, they'll have a nice lap warmer. Clamp the frame rate. Mobile games are often more focused on the quality of gameplay than they are on maximizing the detail of the graphics. Many of these games will set an upper limit on the frame rate, usually 30 or 60 frames per second. If the game loop is done processing before that slice of time is spent, it'll just sleep for the rest. This gives the player a good enough experience and then goes easy on their battery beyond that. How do you control gameplay speed? A game loop has two key pieces: non-blocking user input and adapting to the passage of time. Input is straightforward. The magic is in how you deal with time. There are a near infinite number of platforms that games can run on, and any single game may run on quite a few. How to accommodate that variation is key. Game making seems to be part of human nature, because every time we build a machine that can do computing, one of the first things we've done is made games on it. The PDP-1 was a 2 kilohertz machine with only 4,096 words of memory. Yet Steve Russell and friends managed to create Space War on it. A fixed time step with no synchronization. This was our first sample code. You just run the game loop as fast as you can. It's simple. This is the main, only virtue. Game speed is directly affected by hardware and game complexity, and its main vice is that if there's any variation, it will directly affect the game speed. It's the fixie of game loops. This is what ours is right now. In the GGEZ, in the P5JS, we don't own the game loop. It's set by someone else to 60 frames per second. Fixed time step with synchronization. The next step up on the complexity ladder is running the game at a fixed time step, but adding a delay or synchronization point at the end of the loop to keep the game from running too fast. Still quite simple. It's only one line of code more than a probably too simple to actually work example. In most game loops, you will likely do synchronization anyway. You'll probably double buffer your graphics and synchronize the buffer flip to the refresh rate of the display. It's power friendly. This is a surprisingly important consideration for mobile games. You don't want to kill the user's battery unnecessarily. By simply sleeping for a few milliseconds instead of trying to cram ever more processing into each tick, you save power. The game doesn't play too fast. This fixes half of the speed concerns of a fixed loop. The game can play too slowly. If it takes too long to update and render a game frame, playback will slow down. Because this style doesn't separate updating from rendering, it's likely to do this sooner than more advanced options. Instead of just dropping rendering frames to catch up, gameplay will slow down. Variable time step. I'll put this in here as an option in the solution space with the caveat that most game developers I know recommend against it. It's good to remember why it's a bad idea though. It adapts to playing both too slowly and too fast. If the game can't keep up with real time, it just takes longer. Larger and larger time steps until it does. It makes gameplay non-deterministic and unstable. And this is the real problem, of course. Physics and networking in particular become much harder with a variable time step. Yeah, I was almost thinking that single-player games, maybe this isn't as big of a problem. But then physics could potentially be an issue here. So I guess like even single player games, this is a no-go. Fixed update time step, variable rendering. The last option we covered in the sample code is the most complex, but also the most adaptable. It updates with a fixed time step, but it can drop rendering frames if it needs to catch up to the player's clock. It adapts to playing both too slowly and too fast. As long as the game can update in real time, the game won't fall behind. If the player's machine is top of the line, it will respond with a smoother gameplay experience. It's more complex. The main downside is there is a bit more going on in the implementation. You have to tune the update time step to be both as small as possible for the high end, while not being too slow on this low end. So it sounds like this is the one that's recommended, at least for like most games. This is the last sample code. That would be this one. See also, the classic article on game loops is Glenn Fiedler's Fix Your Time Step. This chapter wouldn't be the same without it. Witter's article on game loops is a close runner-up, and the Unity framework has a complex game loop detailed in a wonderful illustration here. Ooh, I'm curious about what the Unity framework game loop is. Or CenturyLink just takes that over for me? How? Did he like? It's a real link, but I wonder if it's not like it's not live again. It's from 2012. So I'll have to take a look at that later. Also, that reminds me, I'm going to need to set up DNS to not be my CenturyLink. All right, so we're probably, I don't know, we can go, when we implement this, we're only going to implement it in the REST one because we don't need to in the JavaScript one. We're just set. We don't have ownership of the game loop at all. However, we have partial ownership over the REST and GGEZ one. That being said, I'm really interested. I want to take a look. Can we go to GGEZ? Can I, like, is it possible for us to see the game loops here? So I think it's under event. It's like the events loop, game result. So here's the event handler. Here's update. Called upon each logic update to the game. This should be where the game's logic takes place. And then they have the draw. Called to do the drawing of your game. Let me make this a little bigger. You probably want to start this with graphics clear and end it with graphics present. And maybe timer yield now. To wait, to like halt, to slow it down. Interesting that they're suggesting to do that in the draw loop. But one thing that I'm noticing here is even though they have a trait, they have no, they don't have a default for this. Okay, they have the events that we can handle those. They have actually a bunch of these that we can sort of like take over for this. Can I see where this event is being used? For the event handler. A trait defining event callbacks. This is your primary interface to GZ's event loop. Implement this type for and override at least the update and draw methods, then pass it to event run to run the game's main loop. The default event handlers do nothing apart from, okay, like key down event, which will just default exit the game if the escape key is pressed. Just override the method if you want to use it. Okay, so event run. Can we see event run? Here's event run. So while context.continuing, okay, so while we're looping through the games, this must be just a Boolean. If you're writing your own event loop, make sure you include timer context tick. Oh, interesting. So they actually understand that we might write our own event loop, like replace theirs. So this increments the tick. Contact events loop, pull events, takes in a call, a lambda function, no, a closure. We're gonna process event. All right, I'm interested. Where is the update method and draw? When are they called? Here it is. State.update, pass in a context, state.draw. It's at this event. Wait, is that outside of that? It is. Okay. So it's just, they're using the simple method. They're just the equivalent of while true. Like while we're not done, just move as fast as you possibly can. But something that I'm noticing here is they're not throwing update into draw and draw into separate threads. So if I halt update, like if I pause update, that will slow down the draw. And that's a problem. If I want to do a fixed update time step, so that would be this one. We have to figure out what the time is. We calculate the lag. I could throw the update into like the struct and store it, like as the lag, so I can like have the calculation between update and lag there. Or I could have like a different struct, sort of like Maybe arc mutex it. Maybe that's what I need to do. If I start a thread in update and another thread in draw, I can't start a thread in it, right? Because it's calling it every time. I could ignore the update. Danny Fritz, good morning. You had written a multi-threaded game loop in JavaScript that does that a few weeks ago. Awesome. And I keep on forgetting, like, yeah, now multi-thread in JavaScript is now a thing. Are you using workers for that? Or is it like, is it front end or back end? But in GGEZ, we're limited here. It's in the same thread. Update and draw are the same thread. So whatever pausing that I do in update will also pause the draw. That'll keep them at the same, in the same sort of time area. But I do have a limitation there. Can I throw draw into a thread? No, I can't throw draw into a thread because it's going to call this draw function over and over and over again. That will recreate a new thread every single time. Like potentially, I would want a game thread, a game loop that just says, okay, update, you get one thread, state, you get a completely different thread. So can I still do this? Do the lag with that? Did the current, the previous? You know, we might get stuff out of context with this. We'll have to take a look at what we have. But I'm thinking we might just go through all three of these and like implement them one after the other in Rust. But definitely a lot of food for thought for this. It'll be very, very interesting to sort of like see what exactly we want to do for this. So with, don't you occur in synchronization issues? Yeah, that's the other thing. Well, the lag here theoretically will solve the synchronization issues. This one, I think we'll have synchronization issues. This one, I don't think we will. We're going to render at the same time as we update every single time. Actually, you know what? These will be fine. These will not be fine. Okay. All right. Well, we'll sort of play around with this next time because it is after 8:15, which means it's time for me to get ready to go to my stand-up and do my day. But thank you everybody for stopping by. This has been a super informative chapter, and I'm very happy I was able to read through this, and I'm really looking forward to implementing this because limiting the frames per second or actually having the animations correctly has been a thorn in my side for a long time, and I've just sort of tried to do it without really understanding it. So hopefully implementing this will solidify that understanding for us, and then we'll get consistent jumping, consistent animations, everything will be good. So with that, I am going to go ahead and switch over to the ending screen. Thank you everybody for stopping by and watching. I'm doing these streams every single weekday morning at 7 a.m. Mountain Time for about an hour and 15 minutes or so. And tonight is a Node.js meetup. So I used to be streaming that, but I should have the video up online tomorrow or this weekend sometime. It's not anything Rust, so it's not the best thing in the world. But let me a good friend of mine is doing the talk on observable store. Let me go ahead and find the URL for this. I will post that to here. That is, if you would like to come, it's gonna be on Zoom. So basically, no need to be here in Denver anymore. You can join remotely, and then I'll have a video of that up later. Anyways, once again, thank you all for coming, and I will see you all next time, which is probably tomorrow morning. Bye.